Oh, look at that. To understand how you can freeze water without needing to remove energy or to cool it down, basically, there are two sort of fundamental concepts involved in this phenomena where you can get it to freeze under vacuum. One is that their materials have different phases. They're in different phases depending on the temperature and pressure that the material is under. So as you go up in temperature, you sort of get into this region here to the right on this phase diagram. And as you go up in pressure, you go up here. So if you go way up in pressure, everything is going to be solid. If you go a bit lower in pressure but high temperature, you're going to be either liquid or gas, and then vice versa, low pressure, low temperature, you've got solid. Now, there is a little bit of a pressure effect where you see here where you can essentially reduce pressure and stay in the gas phase at lower temperatures. But generally between liquid and solid, you have kind of a straight line where messing with pressure isn't, changing pressure isn't gonna get you your phase transition from liquid to solid or vice versa. You need to change temperature to cross this vertical line here. And the other concept is that temperature is a measure of average kinetic energy of the molecules in a material, meaning that your temperature isn't really a fundamental property. It's just an average of the kinetic energy of every single molecule, the translational kinetic energy, so how fast the molecules are bouncing around. So if your temperature is lower, your average energy will be shifted to the left. And here you can see this sort of Gaussian distribution of energies. And as your temperature gets higher, this peak shifts to the right. So the idea here is that if you start messing with pressure, if you have liquid water, let's say, and you start in the liquid phase, somewhere over here, generally the way that I'm doing this, we're actually right about here at around 25 Celsius, so right at this point. And after the vacuum is pulled and it sits, it somehow ends up over here at a solid. So we reduce the pressure. We're not doing anything to the temperature. We're reducing pressure, and boom, we hit this line here, which separates the liquid from the gas, this phase line. So now we're going to start having molecules, at least part of the water, go into the gas phase. And the molecules that leave first are going to be the most energetic ones. So over here on this energy versus number of molecules versus energy graph, the first molecules that leave are going to be on the right end of these tails, depending on the temperature, obviously. So if we just look at the blue distribution here, you're going to start, as you start pulling vacuum, so reducing pressure, molecules that are to the right will start entering the gas phase. And so as these molecules leave, now this temperature calculation changes because your average kinetic energy is actually lower now. Because the average kinetic energy is the average of basically this whole curve here. And as we start chopping off bits of this curve, your average kinetic energy is going down, so your temperature is also going down. And eventually, you get to a point where on this phase diagram graph, we've moved down in pressure, so we're somewhere over here, let's say. We're generating gas, and as molecules are leaving, our temperature is decreasing because the kinetic energy is decreasing. So now we're shifting to the left on this phase diagram. And once we start getting to this 0 degree point, the water starts freezing. And that's how you end up being able to freeze water without really removing heat. You're just removing the most energetic molecules first, which shifts your average kinetic energy, which in turn shifts your temperature down. Eventually you cross the freezing point and the water crystallizes and solidifies. So that's exactly what we're seeing in the vacuum chamber. So we'll start out with just some basically room temperature distilled water here. And 31.5 grams. And then we'll take the temperature. It's starting out at right about 20 Celsius. All right, we've got this thing loaded in the vacuum, and I'll go ahead and turn the pump on. Oh, and there it goes, boiled over. I guess I'm gonna need to go a little bit slower on the vacuum pull. Oh, that's funny. And not great for the chamber. Alright, let's see how cold this thing got. Oh yeah, it's much, much colder. You can see it fogged up. And it dropped to about 5.9 Celsius. It's pretty good. All right, we'll try this again more properly to see if we can actually get it to freeze though.
boiling again. I'm controlling the vacuum a little bit with the leak valve as well now, just to keep it from being too violent. It's kind of what we do with degassing epoxy at work as well. You pull the vacuum nice and slow at first, just so the bubbles don't get too crazy, and then you slowly start increasing the vacuum as you get more and more of the gas out of the epoxy. Oh, look at that. Hopefully you caught the phase transition, but yeah, it just went to ice. That is really, really neat. Wow, that was pretty cool. Okay. Alrighty, now let's pull it out. And take a look here. Wow. Look at that. Turned to ice. Oh, that's cool. Okay. And take the temperature here. Yep. Pretty close to 0. Yeah. Wow. So here's the solution for not having any water splash out, and just covering it with a little petri dish. So we'll do another 10 grams, give or take. Put this setup in here. Try this again. Let's see, maybe I can get a slightly better shot too. Let's see if I can line this thing up. And it's freezing. Even the little droplets on the outside are frozen now. Frozen once again, at least partially. The top looks like the top started crystallizing. I'm not so sure about the bottom. I don't think that it quite. Yeah, there's a layer of water in the bottom, probably got sealed against the vacuum by the top layer of ice, so it couldn't quite get totally frozen, but that's pretty good. Oh, well, looks like I lost the aluminum foil. Oh, look at that. Hopefully the camera caught that pretty well. Got a little frozen at the bottom here.